Okay, so let's get started with today's session, which is the final session of Basics of Semiconductor Microwave Devices course. So today we are just going to review and see the future outlook of semiconductor microwave devices. So what are the challenges, how those challenges are tackled, and whatever we have covered till date in I should say 12 weeks, we are going to see the basic overview of everything from the beginning. I have just chosen some of the selected topics, some of the selected concepts so that we can review all of those again, so that can help you in your examination as well as in the research or what for whatever the reason you are taking this course. So it's an extra bonus session, and it will be approximately for 1 hour 30 minutes to up to 2 hours, depending upon how soon we finish those concepts. And in the end, I'm going to talk about the research gaps as well as current research areas which are open problems for every one of us to work on. And they are hot topics. They are related to the devices, circuits, maybe some of the mechanical problems, nanofabrication issues, certain problems related to the quantum, and we are going to see all of those. Okay, so I'm Shazan Bhatt, and I'm a PhD student at IIT Bombay in the Electrical Engineering Department, and this course is offered by Professor Digvijay Nath, and we are into the final session of this course today. So, first of all, this was the brief outline what we tried to, I should say, cover in this particular course, wherein we have started from week 1 and we have moved towards the week 12 of this course, week 12, which was the last week Saturday. And we have tried to go from the basic concepts. This was the basic applications, basics, historical overview, applications. Then we studied about the heterojunction physics. That's what we are going to see a little bit briefly about those band diagrams. Then we studied about some of the high frequency, high power devices, which are I should say transit electron devices, gun diodes, showing some fascinating properties, impact diodes. We talked about the avalanche diodes, and then we moved into the 3,5 field effect transistors. And we studied about its physics. We studied about the Johnson figure of merit. Then in the week 5, we talked about the high electron mobility transistors, the MODFETs, which are like the modulation doped field effect transistors. We talked about this particular concept called as 2D electron gas, which is a very important thing in these 3,5 high electron mobility transistors. And this 2D electron gas that makes the, I should say, high mobility or fast operation of these devices possible in the beyond gigahertz regime. Okay. And we talked about the breakdown regimes of these devices. So when these devices are going to break down under high field conditions, so what are those conditions? Then we moved into the something called as p-hemts. Note that here this p is not a p-type or n-type, just like the holes and the electron type. This p stands for the pseudomorphic hems. So we have talked about what is the pseudomorphic hem concept, what are the strains in these particular high electron mobility transistors, so how that strain relaxes, whether it's tensile or compressive strain of the top layer over the gallium nitride, how that plays a significant role in, I should say, uh, changing the performance of those devices. And we talked about the multi-finger devices, field plate technology, wherein you can redistribute the electric field in the device. We talked about the power cell. Then we moved on to the gallium nitride substrate, the stacking of gallium nitride RF, and we talked about the compensation concepts. Then again, we moved into the nanoscale field effect transistor, short channel effects, which is extremely important again. LDMOS, which is one of the most important devices, and it's used in most of the cellular communication devices as well. So people are currently, I should say, modeling these LDMOS devices under extreme conditions, whether it's cryogenic condition or high temperature or low temperature conditions. So there are something called as circuit models of these devices. So we talked about a little bit about the noise, which is again very important. It's a very hot topic almost all of the time, I should say, because you need to understand how the noise implements itself in these particular devices and what are the sources of the noise. and how you can tackle the sources of the noise in these particular devices. And then we moved into the BJTs. We talked about its physics, gain, configuration, the common emitter and common base configuration, what are the output characteristics, and how can we differentiate between the common base and the common emitter. We talked about what are the limitations of those devices and why one is better than the other. Then we moved into the base design, emitter, the silicon germanium heterojunction bipolar transistors. We talked about it. Then finally, in the week 11 and 12, we talked about some basic microwave engineering concepts, including the S parameters. We talked about the Smith chart, which is all this is like going from a Cartesian system, two-dimensional plane to a complex plane containing the impedances in the form of inductances and the capacitances. Okay, then we talked about the impedance matching, and finally we talked about in the week 12 the passives de-embedding concept, which is again important. Small signals, passives includers, the passive devices or passives include inductors, capacitors, wire bondings, all of those other things which are apart from the active device are included in these passives. Okay, so now let's say for example week one. In the week one we talked about let me select this. We talked about introduction to the semiconductor fundamentals, which is again really essential to this particular course. So in this particular week, what we covered was we talked about the band diagrams of the basic semiconductor devices, band diagrams. So we talked about a little bit about how you can draw those band diagrams and why those band diagrams are important. You remember because we talked about a lattice system, which is a one-dimensional lattice, let's say a one-dimensional lattice system, one-dimensional lattice system. I'm just going to tell you how we moved from initial point to the final point of this course so that you can have a map in your mind, just like it should be like a flow chart in your mind that how this course basically will wrap up so that you can have an overview of this course. Okay, so we started with the one-dimensional system of lattice, and then we talked about the its potential. That this is the potential electron will feel in presence of the one-dimensional lattice. Okay, now you can approximate it with somewhat like the rectangular potential wells. These are the rectangular potential wells, and this is just these are the ends of this particular crystal system. Okay, now an electron, for example, here, or electron can be, for example, here. These are basically the electrostatic potentials felt by the electron in presence of the nucleus. Now you take one of these cells, or whatever you call it, rectangular potential wells. This is U as a function of R, and you solve the Schrodinger equation for it. Once you solve the Schrodinger equation for it, you get psi as a function of X. You invoke something called as Bloch's theorem. Bloch's theorem, which is basically says that the wave function at x is equivalent to some e to the power I k a times wave function at x plus a. Okay, so this is basically something called as periodicity condition, which is really essential. So it says that whatever is happening to the electron here, it is happening to the electron on the in the other unit cell, except that there is some phase factor associated with it. Okay, which is this e to the power I k phase factor, and it is where this particular k comes from. This is basically something called a crystal momentum. Okay, now you solve this, you get something called as EK relation, which is E versus K, crystal momentum, or the momentum of the electron. So there's a difference between a crystal momentum and the actual momentum of an electron. So you might have to go again to the basic device physics course, but you can obtain E as a function of K versus the K, which is the momentum, and you get in the first, which is the first reduced zone representation. This is the first Brillouin zone. You get bands which look something like this, this. Okay, it should be like symmetry should be there. Okay, now this particular band is almost completely filled. This is almost contributed by the s-type orbitals, because these bands, what are forming those bands? These are formed by the orbital overlaps of multiple atoms. Just like if you consider this atom, it's having orbitals, s orbital, p orbital, d orbital, e or f orbitals. So all of those orbitals are basically now when for example you combine all of those atoms together in a crystal, they are overlapping, and it's that particular overlap which is basically giving rise to continuum of the energy states. But in the basic sense, actual sense, they are discretized energy values. Okay, and they are having different k points, so that's why they are actually discretized, but there are so many energy levels that it appears us to be as a continuous energy levels. Now this is almost like filled entirely. These are like innermost orbitals, and they mostly don't take part in the conduction process, at least in the low energy processes. So this is, for example, another band which is again filled, but this is the top of this is called as valence band. The bottom of the this band is called as conduction band, and the conduction band is completely empty, at least at 0 Kelvin we are talking about. So at T equals to 0 Kelvin, the conduction band is empty, the valence band is filled. Then if you go on increasing the temperature, or if you externally perturb the system in the form of whether it's electrical perturbation, whether it's light, you're inducing some light on the system, you can excite those electrons to the conduction band, and now electrons become available here. Whatever remains in the valence band are basically the empty states, they are holes, and now you can see that if the electron moves in this direction, the hole moves in the opposite direction. So that's why whenever you apply the force on the electron, let's say in this particular direction, if you apply the force on the electron in this direction, the electron is going to move in the opposite direction, but the holes are going to move in the same direction as that of what should I say, as that of the force. So that's why you say that these holes basically have negative effective mass. Negative effective mass. What does negative mass mean? Negative mass means that there is a if you have a positive mass, for example mass m, you apply the force on this mass, it moves in this direction. This is positive mass. If you have a negative effective mass or mass, if you apply the force in this direction, the object starts to move in the opposite direction. Well, that is the basic notion of this effective mass. And now, why is this picture essential to us? Because using this picture, we obtain, if we talk about the bottom of these bands, the bottom of the top of the valence band and the bottom of the conduction band, they can be extrapolated, and you get the uh, E versus the if energy as a function of position. Energy E as a function of x versus x. Let's say this is x, this is x. Okay, so you get something called as band diagram. This is band diagram. This you call as band structure, or sometimes also called as electronic dispersion, because it shows that how the electrons get dispersed in this material. So that's why sometimes it's written as, instead of E of k, it's sometimes written as omega, because you can write E of k as you can all the time write energy in the form of the frequency, E equals to h bar omega. So you can all the time write omega versus k. So this is something called as electronic dispersion. So now band diagram you get, and this is basically the conduction band, this is valence band, and there is something called as intrinsic level. And then there is, if this material is, let's say, n-type, then there is something called as Fermi level. You talk about these levels. And now again, in order to go from, in order to obtain this band diagram, there is an approach which you can follow by solving the Poisson equation. That's what we talked about in the first week. How you can do, let's say, for example, you have a device, you have a, let's say, P, you have N, you know that there is a depletion region formed here. Okay, then what you do, you solve, you basically you basically make the charge density near the depletion region. You basically plot the charge density as a function of x, and using delta depletion approximation, that means the depletion charges are almost instantaneously terminating outside the depletion region. So using the delta depletion approximation, you get these like delta charges. So this is positive, this is negative, this is q times nd plus, this is q times Na minus, and solving, now you have is like a, it's like a unit step potentials. Now you solve the Poisson equation for it, which is basically dou E over dou x equals to rho over epsilon. You get a triangular type of electric field profile. So this is E electric field as a function of x. And now you again solve for the potential, you get a potential profile something like this. Okay, basically you get something like this. You invert this particular profile. This is V as a function of x. You invert this to obtain energy, which is E of x, which is basically minus q times V of x. You get a profile like this. This is basically conduction band, and then you make a parallel band with a distance, with the separation of the band gap, and you get the concept of this band diagram. And now you can iterate it basically using the concept that the distance of the this basically will give you, this is basically the this will be basically the Fermi level. This will be the Fermi level because this is p side, this is n side, you can see. And this distance basically will give you the concentration. That means EC minus EF is going to give you the electronic concentration. Just like EC minus EF on this side is smaller, so it's going to give you the huge concentration of electrons. So accordingly, you can draw the electronic concentration profiles in these particular devices. Just like, for example, if you have the background, if you have the doping concentration on this side as Na, you have the doping concentration on this side as Nd. Let's not draw in the depletion region. So this portion is depletion region, which is having with WD. And then you have, let's say, electronic concentration here is, let's say, N equals to Nd on this side, complete ionization. Okay. Then towards when it goes inside the depletion region, it drops, and towards the P side, it exponentially reduces because of the recombination. Similarly, that happens to the whole concentration. Whole concentration goes like this, and then it comes like this. Now you can solve it iteratively, something called as self-consistent solution. Self-consistent solution. Self-consistent solution means you should be getting back the original solution. Basically, if you draw the log of concentration of n comma p, you're going to you're going to get back the charge densities, and you're going to see whether they are related with each other or not. Okay, self-consistency means if you are starting from some initial point, then you are going to the final point. Then if you are changing any of the points in between and you are reaching back to the initial point, your solution should be satisfied in a loop. Well, whatever you change in between the loop, it should always be satisfied. Okay, just like, for example, if there is an electron, if there is electron in the and these are holes, this is like, let's say, conduction band, this is valence band. If the electrons are moving, then at every point the electron is moving, their potential is basically changing at that particular point. Okay, because electrons are also contributing to the potential. So at every time you need to solve the Poisson equation whenever the electron is moving, because it's going to change the potential. So whenever it's moving, you have to solve the Poisson. Whenever you have to solve the Poisson, you have to again loop it back. Okay, that's what basically self-consistency means. So that's the simplest way of understanding the self-consistent solution. So these are commonly solved for different problems in these devices. Now, once you get these particular profiles, so why this approach is necessary? Because you get to know about the band diagrams now. Now these are the band diagrams. Now you moved on from these band diagrams to something called as heterojunction band diagrams. Heterojunction band diagrams. Why heterojunction? Because here you don't have any control over the, I should say, band gap. You cannot change the band gap of the system by external potential or something like that. We're not talking about extreme regions. We're just talking about a linear region where you cannot change the band gap by doping here or something like that. But heterojunctions provide you a very good opportunity wherein you can basically grade a junction, you can taper a junction, you can make a different physics altogether. And you can have, let's say, for example, certain barriers for the electrons where the electrons can stay, where you can have confinement, quantum confinement, that can give rise to some exotic quantum effects inside the devices. That is not possible, at least in these particular devices. Okay, so you go to heterojunctions where you use different materials with different band gaps. So let's say, for example, you have aluminum gallium nitride and you have gallium nitride. These are the examples of the heterojunction devices. Okay, and aluminum gallium nitride, again, for example, it has a band gap of 4.0 electron volt. Gallium nitride has a band gap of 3.4 electron volt. So what you do basically, it's basically something called as alloying which we have discussed in details in this particular course. So you have something called like AlX, gallium 1 minus X, nitrogen, and you vary the concentration or composition of the X. This is basically the composition. You vary X, you're going to vary the aluminum concentration. So as you increase the X, the aluminum concentration goes on increasing, the gallium concentration will go on decreasing. And let's say, for example, at X equals to 1, it will convert into aluminum nitride. Aluminum nitride is a highly dielectric material and it has a band gap of approximately 6 electron volts. But it's used here because it's highly polar material. And that's what we have also talked about. And let's say, for example, you have aluminum gallium nitride, then this is aluminum nitride, then this is gallium nitride. So this is aluminum gallium nitride, this is aluminum nitride, this is gallium nitride. You see that as we are moving towards this side, here the x value is 1, here x value is, let's say, 0.2, here the x value is, again, let's say x value is 0 because the gallium is 1. Okay, so by varying the composition of this aluminum metal, something called as alloying, you can basically form this device, something called as heterostructure device, wherein you can have exotic physics now because there is a different band gap. The different band gap will give rise to different bendings, and different bendings will give rise to different states, different energy states for the electrons. It will give rise to different quantum effects for the electrons, where the electrons will be confined in somewhere, they will be moving in somewhere, and that is the basic fundamental notion of moving into the heterojunction physics or heterojunction devices. Now, for example, we moved in from this, we moved into the weak second, wherein we discussed in details about, let's say, how you can form a graded junction, or how you can make a something called as quantum wells. We talked about confinement. So the basic notion was similar. That, for example, if you have a system with which is having a band gap of this, and if you have another system which is having band gap of this, when you combine those two materials, there will be a band bending in such a way that there will be this particular barrier formed, and it depends upon what band gaps you are talking about. Okay, we talked about this in details, that how you draw the band diagram of it. Basically, you have to consider these points to be static initially, whatever these points are, and then you have to draw the band diagram accordingly. Wherever the bending will take place, you will get to know. But you have to consider that all the time whenever you draw the band diagram, the important thing is that these particular things are not going to change, which are the electron affinities. Let's say, for example, the band gap, it's not going to change, although the two different materials will be having different band gaps. So you have to take into consideration that every time, that whenever you draw the band diagram, all the time, that this should be same as this. You cannot change the band diagram. Similarly, this should be same as this should be same, at least on this side. So for the left hand side, the band gap should be same. For the right hand side, the band gap should be same. Similarly, this, for example, if we are talking about the electron affinities as well, should be same, because these are the material constants. You cannot change the material constants by making a device. Okay, just because you are combining or fabricating them, you cannot change the material constants of the constituent materials. Now we talked about these heterojunction devices. Let's say, for example, you have algan, you have aluminum nitride, and you have gallium nitride. We saw that what happens when you combine them, you get a bending like this, then you get aluminum nitride, then you have gallium nitride. And similarly for the valence band, you get something like this. So you get I should say, let me just add a page. Okay, so you get a band diagram which looks something like this. So this is aluminum nitride, this is algan, this is GAN, and the Fermi level runs somewhere like in the middle. So this is like the Fermi level, this is the conduction band, this is the valence band, and almost all of the time, or I should say most of the time, this GAN is basically intrinsic GAN. Okay, because these are like very high band gap materials. So the band gap is 3.4 electron volts. So these are almost like dielectric materials. Okay, except that there is something called as unintentional doping. Unintentional doping. Unintentional doping. Unintentional means you don't want them, but those things happen. Sometimes during the fabrication or during the industry. Uh, can you give me some important notes which will help me to pass the examination? There are no notes in the course. So whatever the notes actually are, they are present in the link I have shared, I guess. The link is shared in that Google sheet. All of my notes are there, but I don't think professor has provided any notes. So you can basically refer to those notes. If you want separate, or I should say my notes also, then I can also add a folder there in the same link where I can provide you my personal notes, which are basically I don't know when I made those notes, but I can provide you also those. Will that work for you? But again, then you have to go through the all of the material instead of just going through the notes. But whatever today, for today, some of the concepts I am discussing, those concepts are going to be important for the exam from the examination point of view. So, so this today's session will be like the overview of the entire thing we have covered till now. And finally, I will be talking about some open research problems, what are the trending topics, so on and so forth. But this will be just like the whatever we have tried to cover till now. It's like the flow chart I'm going to make today, and this I'm also going to share in that particular link by the end of the session. So unintentional doping includes, let's say, for example, sometimes the carbon gets diffused or infused into this. Sometimes the silicon gets diffused. So you have something called as C-GAN. You have silicon dope GAN. So all of those impurities come into these particular systems, and they give rise to certain different properties. Sometimes, for example, C-GAN makes it more, let's say, electron rich, or it produces some traps which can basically trap the electrons. Okay, the carbon based doping produces traps that can basically trap the electrons so that you don't have any conduction in this direction, because the electrons are not flowing in this direction. Okay, electrons are basically present here in this region. This is basically something called as 2D electron gas. I've talked about why this is 2D, because if you have a wafer, which is a circular wafer. Oh, what happened? This is a, let's say, a circular wafer. So if this is the top view, this is the top view of the wafer. And if you make a front view of the wafer, that would look something like this. This is the front view. This is the thickness of the wafer. Thickness of the wafer. So you have different layers. You have aluminum gallium nitride layer. You have aluminum nitride layer. Then you have gallium nitride layer. This is aluminum nitride. This is aluminum gallium nitride. So this is the front view. Okay, I'm just talking about how this looks like. And this is the top view. In the top view, the 2D electron gas is present throughout. I've talked about it multiple times. It's present throughout. Why? Because in the front view, the 2D electron gas is present like just at the interface of L-GAN interface. The aluminum nitride layer is quite thin. It's almost 1 or 2 nanometers. Okay, and we have talked about why this aluminum nitride layer is used, and how you can basically do certain mathematics considering the aluminum nitride layer. And this is basically the 2D electron layer from the front view. And from the top view is present throughout the surface. That means the electrons are not going to flow in this direction. This is not the flow direction of the electrons. The electrons are basically going to flow in this direction or in this direction. So let's say this is X, this is Y. So they are not going to flow in the Z direction, not at all, because there is this barrier. There are these barriers in the Z direction. So this is basically the Z direction. This is something called a growth direction. Growth direction. So electrons don't flow in this direction because there are barriers. Aluminum nitride barrier, algan barrier. Okay. So whenever you have to, let's say, make this device conduct, you make a contact like here. Let's say this is source, you make a contact, this is drain, and then you connect the terminals. Let's say ground this, apply some voltage here, apply some voltage here, and you make the electrons flow in this direction. Okay, so that is the basic fundamental notion of how the conduction takes place. Now you make many of the contacts or many of the devices on this, then you make something called as field effect transistor, and you can also make a gate terminal, or whatever you call it. Then you can control these devices. And by making the gate contact, you are basically depleting this. So these are basically something called as depletion mode field effect transistors. Depletion mode field effect transistors. What does it mean? It means that the electron channel is already present. Electron channel is already present, but what you just do is that you apply some gate voltage to remove or deplete the channel of electrons. So if you have a system like this, I'm just showing the conduction band, and if this is the Fermi level, this is the 2D electron gas. So whenever you are applying, let's say for example some Vg, so let's say you are applying some Vg and you are going on increasing. Basically, it's not a positive Vg, it's some negative Vg. You have to repel the electrons so this is basically the gate metal. So you have to repel the electrons here, these electrons. You have to repel them away from the channel in order to turn it off. So whenever you apply the negative Vg, you basically make this go like higher so that the 2D density reduces. Now this is the band diagram when you have applied a negative Vg. Okay, why this went up? Because you know whenever you apply a negative potential, the electrostatic potential energy of electrons increases, and it went up by bringing all the conduction bands up in the L-GaN, in the aluminum nitride, as well as in the GaN. So once it does so, it reduces the 2D electron density, because now you see that this particular well is not, it is shallow compared to that of this well. This is very deep well. This is deep well. So that's why the 2D density will be huge. So it depends upon how deeper your triangular potential is. The 2D density depends upon that. If you have a triangular potential of this compared to that of this is going to have a huge 2D electron density compared to that of this, because this is highly confined. This is highly confined. You see that why this confinement is here, because you see that this potential is huge, and then there is this potential, this very huge potential. Those potentials are basically confining the electrons in these particular regions. So that's why it's called as two-dimensional electron gas. Two-dimensional because I told you that electron can only move in X or Y direction. It cannot move in Z direction. And electron gas because it's almost just like electron behaves as a gas molecules there. Just like you have the gas molecules with certain average kinetic energy moving, just like the electrons in the metal, just like the free electrons. You can make them move very fast. That's why they are having huge mobility, and I should say, make possible these high frequency devices. One of the other aspect is also that these electrons are basically the peak of this electron. If you have a triangular well, and if this is n equals to 1, which is the first quantum state, I should say energy state of the electron. You have the solution of the Schrodinger equation looks something like this, which is basically mod psi square of x. Okay, so now you see that this particular peak, something called as centroid, it is away from the aluminum nitride layer. This here is aluminum nitride. So it's away from the aluminum nitride interface by delta D. So this delta D we have found it depends upon inversely upon the effective mass. We have also calculated it. Okay, this might be one of the questions in the examination. We don't know, but this is a very, I should say, important concept. And this delta D distance, which is the distance of centroid, that means the electron concentration peaks at a distance away from the interface. Let's say this delta D is 3 to 4 nanometers in case of GaN, L-GaN, HEMTs. And what does it do? It provides you a very good I should say, possibility that now electrons are moving slightly away from the interface so that they are having less drag because of the interface. Now electron can move freely away from the interface. Otherwise, if this is interface, if the electron moves here on this interface near the, if the electron moves near the interface, it's going to face a huge scattering because of the interfacial states. Okay, because of interface states. Interface is like it's a rough surface. It's like a wall. Okay, it's like you have a wall and you have a ball moving on this particular wall. You know that is going to face drag because of the friction. Now, if you have the same wall but the ball is moving somewhere here, it's going to move very fast because now the drag is reduced. Now you only have air drag instead of the friction from the wall. So that's the same thing what is happening to the electrons. Now electrons are moving slightly away from the surface or the interface. That is the important concept we talked about. And this particular delta D, which is basically separation, we have computed it using the two-dimensional density of the states, 2D density of states, and then we considered the Fermi function, and then we computed the concentration of electrons, we computed these delta D, we computed all of those quantities. You might want to go back and look the calculation of it and look what is the dependency of this delta D on the effective mass of the electrons. If you go on increasing the effective mass, this delta D goes on reducing, so on and so forth. And this is very important concept, and this is I should say highly essential for making these devices. Now we entered into the week three. We talked about some high frequency, high power devices, which are the impact diodes, tunnel diodes, gun diodes. Okay, just like for example, we talked about the gun diodes. The gun diode is like, it's not a diode, it's just like a bulk material. Let's say for example, you have gallium arsenide, just gallium arsenide. It's like a bulk material. Instead of combining two materials with p-type, n-type, and making a diode, it's not like that. It's like a bulk material that behaves like a almost like a diode system. It gives you something called as negative differential resistance. How does it do so? It does so by something called as inter-valley carrier transfer. This is when you I talked about in the first slide that when you have the something called as band structure, the band structure of this looks something like this, where these are basically something called as valleys. Let's say this is called as gamma valley, this is called as gamma valley, this is called as X valley. So these are the valleys where electrons can stay. These are like energy levels in the EK space. And if the electron is, let's say, here, it can move on to the other valley upon certain excitation. And the and you know from the basics that the curvature of these is going to give you the effective mass. So more the curvature, less the effective mass. So let's say, for example, this particular thing, the effective mass increases because the curvature is less. So the curvature is less, the effective mass increases. That means mobility reduces, the current reduces. And when the current reduces, what is going to happen? You when you draw the I versus V characteristic, you are initially going to have a high current whenever you apply the external potential. Then you saw a decrease in the current because of this negative resistance. Then you again see the increase. Okay, so this is the region we are talking about. Something called as negative differential resistance. Why does this happen again? Because the electron gets transferred to this valley, and here the electron's effective mass is basically more compared to that of the earlier valley, gamma valley. And then you have basically a lower current, because you know the current is proportional to, let's say, n q mu times electric field. So all of those quantities are going to determine the magnitude of the current, the concentration, the mobility, the applied electric field, so on and so forth. Okay, so this is basically something called as gun effect. It's very established, and it has been established long before. Now people study about it optically as well as electrically in different devices. Okay, now then you talked about the tunnel diodes. The tunnel diodes are basically similar, but you have a tunneling effect coming into picture that gives rise to negative differential resistance. Okay, negative differential resistance is really important because you see from this curve you have a negative slope of this I versus V, and it gives you oscillations basically. So that's how you basically compute or process these microwave signals whenever you have these negative differential resistance. Okay, and what happens basically in these tunnel diodes is you have you have a normal highly doped PN junctions, just like here. But once you have highly doped PN junctions, highly doped P, highly doped N, what you do is that these are basically called as degenerate semiconductors. Degenerate is because the Fermi levels are almost penetrating into the conduction band in the N type and into the valence band in the P type. So the Fermi level goes deeper into the valence band on P type side and deeper into the conduction band on the N side. As a result of which, what happens whenever you draw the equilibrium band diagram, let's say on this side, this is the equilibrium band diagram. So you have huge number of I should say states present on both of these sides. So let's say for example you have for example this PN diode P plus region, N plus region. Then you draw the band diagram which looks something like this. But because the Fermi level is here, so you see there is huge concentration of electrons present here, because this particular EC minus EF is going to determine the electron concentration. Similarly, EV minus EF is going to determine the hole concentration. So there are huge hole concentrations. So the electron now has opportunity to tunnel across and appear on the other side. So this is called as quantum mechanical tunneling, and it depends upon this particular distance also. So this is usually narrow. Why it is narrow? Because depletion region width reduces whenever you have the highly doped region on both of these sides. Okay. Now, whenever you have such effect, what happens is that you get a negative resistance again. So this mostly happens because if you have initially the conduction takes place normally, but then when you start to increase the voltage, this is basically in a non-equilibrium scenario. Non-equilibrium scenario. It does not happen by its own. It requires the addition or the application of the external potential. When you initially increase the voltage, the current increases normally, but then at a certain voltage point, the current starts to reduce and you get a negative resistance. Okay, and then the current starts to increase again. So this particular regime is basically after all the effects have been saturated, the current again starts to increase. So this is not the regime we want. This is the actual regime where the negative differential resistance comes into picture in these tunnel diodes. So there are different phenomena why this negative resistance comes into picture. It can be because of tunneling. It can be because of avalanche devices, something like these devices, which are basically based on avalanche effects. Avalanche effect is like the multiplication or the ionization effect. When the electron goes down the hill of the conduction band, it hits the other electrons, it makes more electrons, so on and so forth, and as a result, you have a change in the current voltage characteristics. So that is basically called as avalanche effect, and that is the fundamental thing of the impact diodes, impact devices. So these devices have been covered in this course from a theoretical, I should say, theoretical point of view. But certain mathematical analysis will be definitely essential in order to understand the deeper aspects of it. I guess some of the maths was covered for this impact diodes. The special class you have done only have your board works. I understand from watching your video, but everything gets mixed up during the revision. I understand from watching your video, but everything gets mixed up during the. Yes, these are the I have deliberately taken some of the snips from my board work, but wherever I have not taken the snips, I'm basically drawing or scribbling on the whiteboard myself, because that just like this stuff I was not I had not taken from my board work, but I have deliberately taken it so that you can relate. Whatever I have shown here, you can go back to those notes and then you can basically relate the in terms of the revision. Okay, so that you have it in a easier sense. You can basically revise the entire thing in a one go. These are just the important aspects I have taken it from my notes, not everything. It's impossible to cover everything. Whatever we have covered till 12 weeks, it's impossible to cover in this particular session. Okay, just like I have just taken away few of the snapshots from those board works. Okay. Yes, definitely. I'll be sharing some notes if possible. I have made few of the notes from my previous session. I don't know whether they are available right now, but whatever the notes I have shared in the link, they are basically present in that particular link. You can go through it. You can go through it anytime. And this thing I'll also be uploading, but this contains almost all of the essential things from which I assume some of the things might be asked in the examination. That is basically that is the notion why I have picked only some of the key concepts and put it into this particular revision session. Okay, I hope that will help. And then we moved into the week 4. In the week 4, we talked about these MESFETs, which are again the depletion mode devices. Depletion mode devices are you have source, you have drain, then you have a gate, and you have the channel already present here. So when you apply certain gate voltage, you deplete the channel. You make those electrons go away from the channel, and then you turn it on and off. That is how these depletion device modes work. On the other hand, you can have enhancement mode devices, wherein you have to enhance the channel, just like you have studied about your normal silicon-based MOSFET devices. Those are enhancement mode devices. Okay, now here we talked about certain concepts like pinch off. They are essential. The pinch off concept, whenever you deplete the channel entirely, you have the channel pinch off and the current no longer flows. You have the huge potential drop at the point of the pinch off, and then you compute all of those characteristics again. and you have something called as pinch off voltage and breakdown voltage you talk about. Now, the important concept here was the concept of this enhancement mode and depletion mode MOSFETs, depletion mode devices, which I have talked about. So this is the characteristics of the enhancement mode device, and this is the on the other hand we have the depletion mode devices. So what is the basic difference is that if you go on increasing the gate voltage, you see more and more current. But on the other hand, in the depletion mode devices, you will have to go in the opposite direction of the gate voltage in order to deplete the channel completely, so that you turn off the channel now. So this is almost like you have to apply some negative, huge negative gate voltage in order to completely turn off the channel. And you have these regimes in it, which are the saturation regime. This is the triode regime, which is basically something called as linear regime. Okay, and then you have the breakdown regime. So the breakdown regime is basically if you have ID, you have let's say some voltage here. It depends upon this is the VDS. So you have initially huge current, then you reduce it, then you reduce it, then you reduce it. So you are increasing the gate voltage in this direction, but in a negative sense. And if you go on increasing the drain voltage, this thing beyond this particular voltage, it starts to break down. So you get a huge surge in the current. Okay. In some of the devices, opposite effect can happen, something called as current collapse. That's also an important concept that I'll be talking about. In those devices, if you have characteristic initially something like this, as you go on increasing this VDS beyond a certain point, let's say we call it V1, you see a droop in the current. This is something called as current collapse. And why does this happen is what we are going to see in the upcoming slides. But these are different effects. A current collapse can happen, a current surge can happen. This mostly happens whenever you have multi-finger devices. Okay, one of the device heats up and it takes all of the currents, and then because of the heating effect. Okay, just because of the heating effect. While this effect is because of the breakdown or because of avalanche effects and ionization, the tunneling and all other stuff. But we are going to check why these particular effects happen. But this is really important effects, and I am damn sure that there will be a question regarding the current collapse concept, because it's a really important concept in today's devices. Why does this current collapse happen? Now we talked about the fabrication. That's a very deeper topic. Even there was no such categorical question regarding the fabrication in the sessions itself. But we talked about a little bit about the heat management and Johnson's figure of merit, which is basically for the which basically gives you the maximum allowable voltage with respect to the maximum transit frequency, unity gain frequency. Okay, so as you go on increasing the maximum allowable voltage, I should say you get a maximum unity gain frequency. That is the basic concept of Johnson's figure of merit. As you see that what is happening basically as you are going from in this direction, you are increasing the band gap, and as a result, your device's voltage handling capacity or capability is increasing, because you see the diamond is highly insulating compared to that of, let's say, gallium arsenide, which is 1.4 eV, silicon 1.2, 0.7, indium phosphide again, silicon carbide again 3 electron volts. So you are increasing the band gap, you're getting higher and higher and higher towards the higher frequencies, and maximum allowable voltage is almost increasing to 1000 volts. You see that there is a huge, I should say, advantage of using these higher band gap devices. So wider band gap helps due to higher maximum breakdown field, something called as critical field. Critical field is it's an electric field which a device can handle, and higher the band gap, higher the field it can handle. Okay, that is the basic layman concept of why these figure of merits are used in these devices. Then we moved into week five. Week five was more of like something called as modulation FETs, modulation doped FETs. So we talked about how why we use these modulation FETs. We modulate certain region where we dope it with certain dopants in order to reduce the scattering effects on the electrons, so that you can further improve the mobility. So you can improve the mobility. Let's say, for example, you dope, if this is, for example, if this is aluminum gallium nitride and this is gallium nitride, we're talking about 3,5 devices, then what basically happens, you only dope this particular region, and this doping is away from the interface. What does it do? It basically, these doping centers are these are impurity centers, okay, first of all. And whenever the electron tries to move near these doping centers try to scatter the electrons. If, for example, initially the electron was moving in this direction, now if you have a doping center here, the electron moves slightly like this. Okay, so that is what scattering is. So you want to avoid it. Why? Because this drastically reduces the mobility. Okay, because this is like a collision event. Wants to move collision free. That is what we ideally want. But these impurities are making it to go under collisions. Now you have another impurity, will go like this, will go like this, and you have those motions or the scatterings in presence of these impurities. In order to avoid it, in order to avoid this particular effect, you dope it away from the channel. You dope it away from the 2D electron gas. This is 2D electron gas, so that you can have less, I should say, carrier carrier scatterings. Okay, but there is one advantage that this particular layer doping there can supply more electrons. If it can supply more electrons, that those electrons are going to remain in this 2D layer, 2D electron gas layer. And if you increase the concentration, you increase the current. That is the fundamental aspect. That's what we want. But there is one effect that can happen. That's something called as remote scattering, remote Coulomb scattering. These impurities can remotely interact with the electrons. Why? Because these are charged particles. Charged particles have electric fields. No matter if you separate them by distance, they are going to influence each other because of electric field. If this is positive charge and if the electrons are present somewhere here, there is, because this is negatively charged, there is certain influence of the positive charge on the negative charge. Because there are field lines coming from the positive charge and they want to terminate somewhere. So they have to terminate on some negative charge. So this is something called as remote scattering, remote Coulomb scattering. This effect is always there. If you want to reduce this effect, you have to again increase this particular d distance, or you have to dope it thin, very thin, just like something called as delta doping. Delta doping, we have a very thin layer, strip layer of this doping, so that you can have a huge concentration of electrons. You can have a huge 2D electron concentration, and on the other hand, you can reduce these impurity scatterings, remote Coulomb scatterings, and other impurity scattering processes. And that's why if you improve the scattering, you increase the mobility. You delta dope it, you increase the concentration. So both of these are they are advantageous to increase the current. So that's what we want actually. Okay, so that is the fundamental notion of these particular modulation FETs or modulation field effect transistors. That is the ultimate concept of it. And this is the particular calculation I was talking about. How you compute that distance of the 2D electron centroid away from the interface. So this is the particular equation. This is very important, maybe there might be certain questions asked from it, and you can see that this distance is inversely proportional to the effective mass of the electrons. Okay, so this is important. You can go through it. I have discussed it in detail in my lecture also, and in the notes I think I have clearly shown it how you can derive it using the 2D electron density of states, the Fermi function, and the calculation is quite simpler. And yeah, this thing was discussed in detail. This is about week 5. So week 5 is all about it. And what we did, so these are the important aspects of the week 5, which are really important, which can be asked in the examination. Now we moved into the week 6. Week 6 was more about p-HEMTs, which is something called as pseudomorphic HEMTs. These are like strained layers which are present on the top of the actual active device, or top of the actual layer, that can basically strain these particular devices, and it can induce or increase the mobility times ns product, which is basically the goal. Okay, so this is something called as strain engineering. You can basically strain certain layers, tensile stress, or compressive stress. It depends upon the choice of the material, the lattice constants, and the other things. So if that happens, you can basically create certain, I should say, you can basically modulate the mobility of those electrons. Okay, because why does this happen? Why does the strain or the stress have effect on the mobility? Because you see, whenever you draw the band diagram, whenever you have a band diagram, let's say this is a direct band gap material, this is the conduction band edge, this is the valence band edge. So what happens is basically these all quantities, the energy values, or even rather in even the energy gap, which is the energy gap, they can be changed if you apply some pressure to the device. The pressure is basically stress. Okay, if you write stress in terms of force per unit area, you can also define the pressure in the similar sense. You can have strain, which is change in the volumetric change divided by the original volume. So there is something called as deformation potential. Deformation potential is basically if you have let's say for example the variation of the band gap with respect to, let's not say band gap, variation of conduction band edge with respect to applied strain. You can define it some constant dE, which is something called as deformation potential constant. This is deformation potential constant. So it is the variation of the band gap with respect to strain. You can write it in terms of pressure also. You can write it as, let's say, dou EC over dou pressure, but there will be Bulk's modulus of elasticity. So these are the mechanical quantities or equivalents, but these are not exactly determined classically. These are quantum mechanically determined, these potentials, deformation potentials. So these potentials, deformation constants or deformation potential constants tell you how much the energy value change with respect to the stress or the strain you apply on the system. And whenever those energy values change, the electron's energy value changes. That's as simple as that. And whenever the electron's energy value changes, you know that it can do all sort of crazy stuff. Because that is what defines the electron. It is just the energies, energy levels. Okay. So that is basically the concept of deformation potential. And what else was covered in this is, let's say, for example, you have certain, for example, we talked about we talked about the device configuration wherein you have let's say a source, you have a drain, you have a gate, you have a feeding line. So whenever your gate is feeding certain microwave towards to the devices, just like this, it depends upon the length of this feeding line and all other dimensions, that how this microwave will reach to the other end of the devices. Okay, because it's going to bring the phase changes, it's going to bring the other shifts in the frequencies or the phases of these particular microwaves. Okay, just like if you have a multi-finger structures, just like if you have multiple devices, you have source, you have drain, you have again source, you have drain, you have source, you have drain, and there is a single bar of gate which is feeding all of these devices. Okay, so whenever you are feeding the microwave to this gate, you are feeding it somewhere here. It's going here, it's going here, it's going here. But because the gate length is so huge that there will always be some phase delay or the delay, let's say delta t, between the two waves propagating in the different these lines. Okay, because of that delay, there is a phase. Basically, phases are changing. So you need to accordingly consider what should be the dimension of this bar in order to reduce those phase changes. So that is what basically we discussed. So we discussed about the limitations that this particular width of those metallic regions should be much less than the almost lambda by 10, which is the microwave wavelength. I mean, 1/10 of the wavelength in order to avoid those phase changes and in order to, I should say, avoid any of those delays happening. And you know that delay can always happen because the microwaves are moving, let's say, with the speed, with some certain speed inside these particular metallic regions. If let's say they are moving a certain speed of light, then the delta t will be approximately equivalent to it will be approximately equivalent to L over speed of light. So that is basically the change in the delay. Accordingly, you can convert it into the phase change. Okay, the phase change is basically it's like I should say almost like e to the power I omega t minus kx plus minus kx plus some delta phi. Okay, you can all this is basically certain phase gathered inside by the plane wave. I'm discussing it in terms of a plane wave. Okay, so let's say for example you have if for example you have at x equals to L, you can write k times L is equivalent to this k is basically 2 pi by lambda times the L, which is basically uh, the length of this particular region. Then you can basically find what is the something called as phase difference of the microwave present at the different sections of this particular device. It's just from the basic electromagnetic waves. There is no jargons or there is no rocket science present here. It's from the electromagnetic wave equations. Whatever the electromagnetic wave equations happen to be in the, let's say you are using it in the free space, you have to apply the same here, except that you have to consider the permittivities, permittivities of the medium as well, because it's now certain material with certain epsilon, with certain mu, and you have to consider all of those things. And what are the other things present here? Yes, we discussed about this is really important. This is something called as metamorphic Hemts. The metamorphic Hemts, instead of using the earlier structure, which was like this, okay, now you use another layer here, which is like the blocking layer. Okay, that is what is basically the concept of this something called as composite layers. And what happens is basically you have advantage because this is a huge, high band gap material, so it's going to give you good breakdown voltage. And this is for example low band gap material, so it's going to give you good conductivity because the electron layer is present somewhat here. And if you go on increasing the gate voltage in the negative sense, you're going to make the band diagram look like this. Okay, so that means these electrons are slightly going to shift towards towards the other end. Okay, so you can modulate or you can have a better confinement in these devices so that you can have I should say better mobility, less scattering, and greater breakdown voltage. That is the fundamental thing of these. That is the fundamental important concept of these composite layers or metamorphic heads. Okay, this particular thing is having this is something called as two channel devices. These there is first channel, then there is second channel. Second channel almost appears somewhat like here. This is also the electron density. That's why these are called as two channel devices. Two channel devices. This is the first channel here, which is the 2D electron gas. Then another electron channel is somewhat here. But this is the first channel to respond. Okay, and these channels they provide basically different advantages. High band gap means the high breakdown voltage, which is very essential. Okay, so this particular thing is again this is a low band gap material and it provides you good conduction and it provides you good huge concentration of the electrons, and also the electrons are coming from this end. So there is all sorts of advantage in these metamorphic devices. Okay. Now that is about week 6. Then we moved into the week 7 and we started to study full-fledged GAN Algan HAMs, which are basically the workhorses of these microwave devices in today's world. So these are really, really essential in today's world. We're talking about GAN Algan HAMs. And I talked about it. How does the GAN Algan HAMT look like? You have some substrate. It depends upon whether you have silicon nitride, you have silicon carbide. They give you different advantage over the another. That's what we have discussed. You have certain nucleation layer in order to protect the electrons, and also in order to separate, or I should say make a less conductive pathway in order to stop the leaking path from the so that the current should not leak away from this surface towards the substrate. And this nucleation layer above it, you have a doped GaN, you have intrinsic GaN, then you have aluminum nitride layer, which is very thin, so that you can have huge polarization. So those polarizations are important because that is the essential thing that brings in the charge to the 2D electron gas. If you have a structure which is aluminum gallium nitride, gallium nitride. Aluminum nitride is highly polar, and there is spontaneous polarization, there is piezoelectric polarization. Spontaneous polarization I have shown here. Have I shown it here? Yes, no, not here. Spontaneous polarization occurs because of the electronegativity difference between the nitrogen and the gallium. As a result, the nitrogen appears to be more negative than that of the gallium, and the piezoelectric polarization appears because of the straining layer. Okay, you have strain of the top aluminum nitride layer over the gallium nitride layer, so that you can have this polarization effect. Okay, that means charges are basically induced. That's what polarization is. So because of it, you have a huge piezoelectric polarization here. It makes this end plus Pz, slightly, I should say, highly positively charged because of piezoelectric polarization. And this end, it makes it negative because of piezoelectric polarization. Also, there is spontaneous polarization charge here. There is spontaneous polarization charge here. Because of aluminum gallium nitride, there is spontaneous polarization charge on this side. There is spontaneous polarization charge on this side. Gallium nitride is also having spontaneous polarization because it almost looks like this. Not exactly like this, but it is also it is having spontaneous polarization charge because the nitrogen is highly electronegative. This is slightly electropositive. So you have sigma z because of the this is minus sigma z because of gallium nitride, plus sigma z because of the gallium nitride. But because this gallium nitride thickness is considered to be large, so the effects of these is considered to be negligible now. Okay, because whatever the field lines was coming from the plus sigma z charge, whatever the field lines was coming from the plus sigma z charge, that will be somewhere balanced or negated by the negative charges. Those field lines will terminate on the negative charge. That is what basically means that if you have a large thickness, then your I should say these spontaneous charges are not going to play any role. But what remains is these charges, piezoelectric charges, spontaneous charges, piezoelectric charges of aluminum nitride, and it brings this band bending here. Okay, and these are the charges which actually bring the electron to this 2D electron gas here. And that's how the 2D electron gas forms in these devices. Okay, so that happens when you make the contact, when you just combine the devices, when you just combine the layers, the almost spontaneously those electronic charges or electrons come and sit at this particular place and form this layer of electron, which is basically a 2D electron gas layer. That is the basic notion of how the 2D electron charges come into picture. So this is the concept of general concept of these algane-Hertz. Then you have again the same Johnson figure of merit, which is basically the breakdown voltage versus the unity gain frequency, how it basically comes into picture. And then you have field plate technologies. Field plate technologies are just to modify the electric field profile coming from the gate and the drain. Just like if you have a device, if you have a source, you have a drain, you have this, let's say some dielectric, you have some gate electrode, then you can deposit one more gate electrode over it. You can do it layer by layer. These are called as field plates. Obviously, there is some separation between, so that you can basically whatever the field is coming from the drain, you can terminate on these gate plates, so that you don't have a coupling of the gate and the drain. Okay, why is this important? Because you see that these distances are very small. We're talking about nano fabrication processes. These distances are very small. You can basically engineer these electric field profiles, which are coming from different contacts, in order to terminate it effectively, so that there will be less capacitive coupling. If there is less capacitive coupling, there will be less delay. If there is less delay, you have a faster device. That is the fundamental notion of these field plate technologies. Now we talked about certain emerging topics in it. So one of the emerging topic was something called as n-polar HEMTs. N-polar HEMT is something called nitrogen polar HEMT. Okay, nitrogen polar HEMT is like, it's like inverting the entire device. If you had a gallium nitride, let's say you have a gallium nitride wafer. If you look at the front view would be something like this. This is the thickness of the wafer. All the time the up top of the layer behaves positively, the bottom of the layer behaves negatively because of the spontaneous polarizations. I talked about it. Just like this thing. So this is like the top of the gallium nitride. No, this is like the bottom of the gallium nitride, and this is like the top of the gallium nitride. Okay, the top behaves like positively, the bottom behaves negatively because of spontaneous polarization. Now you invert this and you have something like this, negative, positive. Inverting means you have a this has to be entirely fabricated by molecular beam epitaxial process or MOCVD processes. So this is very emerging technology in today's world. Now you have a top surface which is negative and you have a bottom surface which is positive. So this is something called as N polar or nitrogen polar HAMT. N means nitrogen. That means most of the nitrogen bonds will be here. And so that makes the top surface appear to be almost like a negative. And when you have such structure, you have inverted the entire band diagram. Instead of the band diagram, something looked like this before. Now the band diagram looks like this. Now you have 2D electron gas here instead of here. You see, this is like flip. Now, what is the essence? Essence is that because this distance, this is a gate here. This is gate electrode. Now the distance of this 2D electron charge from the gate is less. So you have a better control over the channel. You can turn it on and off quickly and you have a faster operation. Okay. That is the essence of these n-polar devices, and these are right now largely trending, and people are trying to fabricate these n-polar devices instead of the normal, I should say, gallium polar devices. Though gallium polar are the normal, but this is the n-polar devices. This was about the week 7. Now we moved into week 8, and towards the week 7, week 8, the things started to get a little bit easier, I should say, in terms of the concepts. Because now here we talked about the gate length terminologies, something called as short channel effects, and some of the short channel effects you have talked about in your MOSFET courses. You have talked about something called as drain-induced barrier lowering. You have talked about velocity saturation effects, VSAT effects. You have talked about leakages. Okay, you have talked about something called as gate-induced drain leakage. Okay, gate-induced drain, is it leakage? Drain-induced barrier lowering, gate-induced drain lowering. I guess it's lowering, not the leakage. Leakage is something different. So you have talked about all of these effects, but the important effect which was basically studied here was Dibble, that the drain, because you are applying huge voltage on the drain. So if you have a source, you have a drain, you have a gate here. So this is the channel. This is the front view of the device. If you draw the band diagram from the front view, it looks something like this in equilibrium. So this is the conduction band. This is the drain side. But because you are applying such a huge voltage on the drain in these devices, because these are high power devices, your bending will be somewhat like this. That's what you expect. You expect that this channel region should not be impacted by the drain. This region should not be impacted by the drain. But what happens because you have applied such a huge voltage, you get a droop bending in the channel region also. Now the channel reduces. Now you have an effect on the channel region also. You see this particular region because of the drain voltage. That is what is basically called as drain-induced barrier lowering. And now the electrons start to move towards this channel very, I should say, drastically. There's a huge increase in the current, and that is detrimental for the big breakdown. So that's why you want to basically, the important, if somebody tells you what is the important parameter in this device, it is this distance, the LGD length. It is very, very essential in these devices, because it's going to determine the breakdown, it's going to determine the unity gain frequency, it's going to determine the transconductance, it's going to determine the unity gain frequency, it's going to determine the how fast the device is going to work, it's going to determine the delays, all other things that is basically determined by this LGD distance. So that is the essential point. So that's why people try to make it somewhat like this, asymmetric. Source, drain, you have a gate, so this is LGD, this is LGS. So people try to make it closer to the source so that you have better thermal management. Because whenever the electrons are moving in the channel, they are also heating up so that the heat can dissipate towards this end more effectively. So people have done research on it. This is also open research problem. This is something called as thermal management. Okay. So all of those effects are essential. Right now, I may be going a little bit fast, but you can all the time watch this video on your on my YouTube channel, and you can look back these effects and you can think about these effects one by one, because these are really essential effects. And that is the essence of putting these videos on the YouTube, so that you can basically pause, you can think, you can write, you can note down, and you can maybe slow down this video a bit because it's really difficult to cover everything in 1.5 or 2 hours because we have covered a lot of stuff in this course. Then there was something called as reserve technology. I won't go deeper into this reserve technology again because it will confuse you here a lot. I have discussed it in one of the questions that was asked in the assignment section, and there's a very huge probability that there will be a question asked from this reserve. Reserve is almost like a technique where you have two depletion regions, a bottom depletion region, a top depletion region in the devices like LDMOS, which is basically literally diffused metal oxide semiconductor, which looks something like this. Okay, so you have two depletion regions. One is this depletion region, another is this depletion region. So you want one of the depletion region to completely fill the other part. So you want this depletion to be fast compared to that of this depletion, so that you can have a huge breakdown voltage. Okay, once the depletion region is made, you can give a lot of voltage to that particular device. Okay, because it's not, when once the depletion region is formed, it's just like the device behaves like an insulator now because there are ions only present in that region. You no longer have the free electrons there. That is the concept of reserve. I don't know what is the full form of it. Remodulating. I don't know. The full form doesn't matter. But the concept is that you want to improve the critical breakdown field because of faster moving, faster forming depletion region from the bottom to the top compared to that of this lateral. Okay, that is the concept of this reserve technology, and it's really essential in these LDMOS devices. Let me remove this. Now, what is this? Now what? Now we moved into week 9 again. This week 9 is also it's if something is really important after week 6, or I should say week 5, that is really week 9, because in week 9 we cover the BJT. And BJT, if somebody tells you that BJT is not being used nowadays, it's just he or she is just fooling you because these are hell lot of used in all of the I should say commercial and defense applications. Although it's now replaced, it's now being fastly replaced by the gallium nitride or gallium nitride based technology, but these are currently used in the areas where those devices fail to perform. Because one of the essential importance of these BJTs are that you can make them work at high frequencies and high power also. That is the essential I should say thing about these BJTs. Now, the essential thing about these BJTs was you want only one of the current component to flow, something called as forward injected component. You don't want the backward injected component to flow, something called as hole component, so that this device should be dominated by electrons only. Okay, so that was the concept we talked about, how do you stop the back injection of the holes. Okay, so for that we talked about something called as, where is that concept? Okay, I'm not shown it here. Okay, I'm not shown it here. But if but yeah, we can look whether I've shown it. Yeah, this is the concept I was talking about. So how do you stop the back injected component of the current, back injected holes? You make a heterojunction bipolar transistor. Okay, earlier your BJT was looking something like this. This was the band diagram of the BJT. This was emitter, this was base, this was collector. Base region is quite thin. You have the electron getting here, but the holes also went here. You don't want this thing to happen. So what you do, you make a barrier at this region. How do you make barriers? You use heterojunctions. Heterojunctions. That is the essential importance of heterojunctions. Heterojunctions give you, I should say, freedom to trap electrons, to make barriers, to confine the electrons, just like playing with electrons. Okay, so you move on to something called as HBTs, heterojunction bipolar transistors, and you make a device which is having you make a layer which is having, you make emitter from a semiconductor which is having higher band gap, you make base with another layer, you make collector with another layer, as a result of which you have this huge barrier present here. and that stops the back injection of the holes. These are the holes, so they no longer can back inject into the emitter. So what happens is that you have drop in the injection hole current, and as a result, your performance increases. But because now you have a faster device. Why you have a faster device now? Because now you have a unipolar operation. Unipolar operation. Only the electrons are moving in the forward direction, and electrons are faster. Mobility is much greater than that of the holes, and that is the essential aspect. So you want to make them unipolar as much as possible. Okay, so that was the essence of moving on to heterojunction bipolar transistors. You see how the story is making sense. We went into BJTs, then we studied about BJTs, but then we saw that there is a problem that you don't want the back injected component to be there. Okay, so what you did is that you moved on to the HBTs in the week 10. There was one important concept which was something called as Kirk effect. And this Kirk effect happens in both of these HBTs as well as BJTs. So this happens, but this happens mostly under high injections. High injections means whenever you have very high collector current or emitter current flowing in the system. That is what these high power devices are basically. Okay, so what happens because of it? Whenever you have a very huge drastic current flowing in these devices, you have something called as base push out effect. So what happens is at this particular region, you have a depletion region. And if you draw the charge profile and then you draw the electric field profile, that looks something like this. This is the electric field. Now, if you go on increasing the VEB, which is this voltage, let's say this is this particular voltage, VEB, okay, you go on increasing it, you are going to make, what you are going to do is that you are going to increase or reduce the slope of this particular electric field profile. It just comes from the Poisson equation, from this. So if you go on if you write the Poisson equation, that looks something like this, where this is the JC is the collector current. This is these are basically immobile charges, which are depletion charges. So if you go on increasing VEB, the emitter current increases. That means the collector current increases. If the collector current increases, the JC by QV sat component increases. This component. And because there is a negative sign, increasing this would mean reducing the slope. That's what is basically happening. You're reducing the slope as you are increasing the VEB. Okay. So what happens is because of it, the base width basically increases. There is something called as base push out effect. Base push out decreases the current, decreases the decreases the unity gain frequency. It increases the delay. So what is base push out? So once you start to increase more and more of this VEB, you start to completely get a flat electric field profile. Okay, so that the entire collector is depleted now at this point. Whenever you have a flat electric field profile, that means you have a fully depleted collector region. And means this region is fully depleted now. Once you start to increase it further, now what happens is because the slope of the electric field starts to change because now this term starts to dominate. Okay, because now the collector was fully depleted. Now that term is gone. Now this term starts to dominate. And you have the inversion of the slope of this. Initially, this was negative slope, zero slope, positive slope. Now the slope starts to increase. Okay, slope starts to increase. This is positive slope, and it starts to increase so much so that there is a point in the bit near the base collector junction that electric field becomes almost equivalent to zero. Okay, and what happens because of it? It starts to spill holes into the collector region. It starts to transmit, I should say, move the holes into the collector region. So that is something called as base push out. And it is almost just like a injection of the holes towards the collector instead of the emitter. It's just like the opposite effect. And that kills the current. Because that kills the electrons. Holes are detrimental for the electrons because recombination happens because of electron hole pairs. If there is no hole, you don't have any electron to recombine with. Okay, that is the single important aspect. So that reduces the gain and that is detrimental. Okay, so that is basically something called as Kirk effect in these devices. And now we also saw that how you can basically mitigate, how you can protect your device from the Kirk effect is that you have a, let's say this is the Fermi level on emitter side, this is the Fermi level on the base side, this is the Fermi level on the collector side. You make the device something like this so that you can have electrons go here, you can have electrons go here, so there will be no base push out effect. Earlier it looked something like this. It was like the Fermi level was here, the Fermi level was here, and the Fermi level was here. Okay, so the electrons moved somewhat like this. Now you have bring this particular region up. How you can bring this particular region up? You can negatively bias it, because you know if you negatively bias this region, the electron's potential energy rises, the Fermi level goes higher. So now you can protect your device from the base push out effect. So these are certain effects, aspects how you can engineer these Kirk effects. Now we moved into the week 10. We talked about the HBTs and what is basically the we talked about important thing, that is current collapse. This is the important thing I was talking about. Instead of current going like this, which is breakdown, the current goes like this. This is the basically output characteristic I am showing. This is something called as current collapse, and it happens because of heating effect. Whenever you have a multi-finger structures in these HBTs, this is HBT, somehow those fingers heat up, and if one of the, because heating, this heating is almost like a, it's a very highly non-linear phenomena, and you don't know which finger is going to heat more compared to that of the other. I'm talking about metallic finger. So if one of the finger heats up, it starts to draw more of the currents, and it heats up more. But what happens is, because if the temperature increases, the back injection barrier reduces. Which barrier I'm talking about? I'm talking about this barrier, the back injection barrier for the holes. Okay, if it reduces, the beta starts to decrease and the current starts to reduce, because holes start to get injected, and now your overall current starts to reduce. So finally your current becomes almost negligible, temperature also starts to reduce, and the equilibrium is attained, so that your device does not get damaged, but your current operation or device stops, I should say, working. Okay, or it stops to produce any of the gain or any of the desired output, but it does not get damaged. This is opposite to that of what happens in silicon. If you have a silicon device, instead of HBT, if you have a silicon based device, then in silicon there is something called as positive feedback happens. If the temperature starts to increase, the IC starts to increase, it further increases the temperature, and this results in something called as breakdown, or not breakdown, it results in something called as thermal runaway. Something called as runaway, thermal runaway, and it completely destroys the device. So that is the important factor why HBTs are important. HBTs are necessary, advantageous compared to that of silicon-based BJTs. Okay, that's why this current collapse concept is completely, I should say, very, very essential in these HBT devices. Okay, this is about it. Then we talked about, there are certain there are certain components of the base current. What are those components? The base current is composed of recombination current, the space charge limited current, injection current, the surface current. All of those are very essential. How does they come into picture? That's what I should say, I have deeply discussed this concept in my week 10 session, wherein each of the component has been discussed in detail. How does the recombination take place inside base? How does surface current, because of the surface charges or the surface defects, they basically reduce the overall current. So that is essential for the base current, and that is going to affect the gain, which is beta. Okay, so this is really again important. What are the essential components of the base current? Then we moved into week 11. Week 11, I have not included any of the board work here because it's completely messy. And for week 11 particularly, I have provided my notes. So for week 11, my notes have been provided, which are basically handwritten notes for that particular session. But here, what we discussed is that we discussed the two-port networks. You have a two-port network, you have certain input voltage, you have input currents, you have output currents, you have output voltage. So how you can define certain something called as Z matrix, how you can define Y matrix, how you can define ABCD matrix. We have not defined these things. How you can define, let's say, H matrix. These are just like inverse of each other. And ABCD and other higher matrices, also the S matrix, which is basically the S parameters. So these things have been discussed in week 11. But essential, if somebody tells you what is the essential important concept in these, it is this S matrix as well as this Z matrix and Y matrix. Because using this S matrix, you can basically form a matrix which is S11, S12, S1, S21, S22. So these basically determine their reflection and transmission coefficients of a device. So they are basically essential because if you have a device and if you have microwave coming in, so this is incident microwave, you have some reflection of the microwave and you have some transmission of the microwave. So these coefficients tell you mathematically that what is the ratio of, let's say, reflected to incident, what is the ratio of transmitted to incident, what is the ratio of transmitted to reflected. So it is just the mathematical convenient way of defining these ratios. Okay, so that is what these S parameters basically give you. And we have discussed about these S parameters. We have discussed about the waveguides, strip lines, and the microstrips. So we have discussed about this concept that if you have a substrate with certain refractive index epsilon, let's say epsilon, with certain thickness h, you have a metallic strip over it, which is having the width w, then this basically acts like a something called as microstrip line. Microstrip line is just like a waveguide. So that the microwave basically, if you feed the microwave, that travels along this. But because the microwave is like having the electric field and the magnetic field, so the electric field basically leaks to the air space as well as into the substrate. You want most of them to be inside this, most of them to be inside substrate. But because there is certain leakage into the air, so let's say this is air, epsilon 1, this is epsilon 2. So you engineer the thicknesses W by H ratio in order to change something called as effective permittivity. This is basically takes into account the permittivity of air and the permittivity of the substrate. So you have a plot of effective permittivity versus the dimension W by H ratio, and it goes on something like this. If you draw the impedance on the same curve, the characteristic impedance, it goes on something like this. So characteristic impedance as well as effective permittivity, they are all dimension dependent. So these dimensions are really essential in these waveguides or microwave strip antennas. This is the same theory as in microwave strip antenna theory or microwave propagation. That is the same aspect what happens in these microwave devices. Okay, that's what we covered. We also covered Smith charts, which is very, very essential in these devices. Smith chart is just like you are going from a Cartesian system towards the circular polar coordinate system, where you define inductances, you define capacitances. So it's like a polar plot. But it's an art to read these plots. So you have certain impedance lines, you have certain other plots, other lines which are basically which define basically the admittance and the impedances of this particular of the microwave system, from where you can basically obtain the inductances, capacitances. Resistances are not mostly shown because they are lossy components. Okay, so knowing this, you can actually obtain the inductive impedance, which is basically the reactances. Okay, this is basically omega times L. This is 1 over omega times C, the magnitude I'm talking about. So Smith chart is an essential. Maybe there might be a question or two. There is a higher possibility that there may be two questions from the Smith chart. I'm just guessing, but this is really essential because Smith chart concept is you might be given a Smith chart and you might be given a point on the Smith chart and you have to accordingly locate the point on this particular Smith chart. And there are two types of it. There is an impedance Smith chart. There is an admittance Smith chart. The admittance Smith chart is like the opposite. Admittance Smith chart is just like the opposite of the impedance Smith chart. If you make the if you make the impedance Smith chart just like this, you make the admittance Smith chart on the opposite side. That is the fundamental thing about these Smith charts. Okay, now we moved into the week 12, which was basically mostly about the passive devices. So the passive devices in the microwave circuits. Passive devices are such components which are just there, which don't ideally consume any power or which don't require external supply of the energy source. Okay, those are the passive devices. Those include inductors, capacitors, wire bondings. Maybe these include other components which are basically apart from the active device, which are basically present there. So if let's say if this is the active device, so if, for example, if I make it like this, so if this is the active device, this is the active device, then you have these pads, metallic pads, which are the ground pads. Then you connect, let's say, a drain pad. You have a gate pad. This is gate. This is drain. This is, let's say, source. These are grounds. Okay. Then you can connect. If this is the active area, then you can connect basically certain wires, wire bondings. These are all included in passives. Okay, except the dark blue region, that is the active device. All other things are basically computed in included in the passives. And the important thing about these passives is that they bring in inductances and capacitances and resistances in the circuits. Okay, so now whenever you draw the equivalent model, you have to model it as a inductor, capacitor, resistor, all of those networks. That is what basically is shown here. Let's say if you have an inductor, you can model it using this equivalent circuit. Because inductors are having resistances because of the metal, it's having capacitance because those inductors are inductance wires are closely spaced with certain separation, so you always have a capacitance. Okay, and how those inductors are made on a microfabrication level on an MMIC, you have something called as spiral inductors. We also talked about it. So the spiral inductors are really essential in order to couple the microwaves. Okay, and they also give rise to capacitances. They give rise to resistances, and inductances are always inherent to it. So you can model those spiral inductors as well. And then the important factor we talked about was Q factor in these devices, which is basically the quality factor. It is the ratio of something desired to something undesired. Okay, you might have studied quality factor in other aspects like in resonance, and maybe that was in class 12th. But quality factor is essentially in layman's sense, it's something what you desire and something what you don't desire. And we talked about something called as this is self-resonance frequency. Self-resonance frequency. It is the frequency beyond which inductor no longer behaves as inductor. It almost behaves like a capacitor. Okay, that is weird, but that is what happens. But that means the inductance becomes negative beyond this point, and the quality factor drops significantly. And at exactly the self-resonance frequency, the quality factor becomes zero, then it starts to reduce. That is the fundamental aspect of the quality factor. You want this quality factor to be as high as possible. That's where you want your inductor to perform. This is the region where you want your inductor to be in this particular frequency regime. So that's why the frequency is essential. So that's why it's not you cannot give arbitrary frequency to a device. Okay, you cannot just keep on increasing the frequency to your device, because what might happen is that those inductors can behave weirdly, and you can get a drop in the quality factor of the device because of the negative inductances. Okay, so that's why the frequency operation is essential. We talked about skin effect. Skin effect mostly happens with the ACs, alternating currents, and the alternating voltages. Particularly, we are talking about here microwave signals. Those are electromagnetic wave signals. So this effect is going to happen in these signals because of something called as back EMF gets developed. Okay, and that basically makes the current to flow on the outer periphery of the device. Okay, so there is only a slight depth up to which the current can penetrate into this device. That is called as skin depth. And this skin depth is a frequency function of frequency. So that if you have a zero frequency, nearly zero frequency, which is basically DC, skin depth is, I should say, infinite. That means entire conductor conducts. If you have a conductor and if you feed it DC, entire conductor is going to conduct. The electrons or the current is going to be moved in the entire conductor. Instead, if you have a AC, then only the outer peripheral regions are going to mostly dominate in the conduction or the current flow. Okay, so that is why there is a, if you see, if you have some wire which is carrying the AC current, and if it goes on for years and years and years, you mostly see that there is wear and tear, or the wire starts to degrade only on the external surfaces. And if you open the wire internally, the internal portion of the wire is almost entirely, I should say, completely new. I'm talking about the bulk region of the wire. The reason is because of the skin effect. The AC mostly flows onto the surface of this particular conductor. That is the essence of this particular skin effect. Okay, and then we talked about that was it about this particular sessions, and we ended this session with something called as de-embedding concept. De-embedding is you consider only the active device and you subtract the parasitic effects of all the external devices which are connected to it. You subtract its resistances, inductances, capacitances, and that is basically something called as de-embedding. You only consider the resistances, capacitances, and inductances of the active device. Whatever is on the periphery, you remove that in your calculation. That is the concept of de-embedding. Okay, that is where we finished. Now we are into the research problems and the trends in this, I should say, in microwave devices. What are the current trends? Where are people working internationally as well as nationally? So there is no doubt there is a huge interest in these microwave devices because it has applications in defense. It has applications in a commercial domain. In It has applications in tactical domains. Because where are they required? They are required in radar. They are required in, I should say, EVs, electronic vehicles. They are required in jammers, which are basically certain components which jam the signal. They are required for antennas. They are not antennas directly. They are required for microwave processing, signal processings. They are required for drones, and they are also required for quantum computing, let's say some cryogenic applications. Because in quantum computing, you also require microwaves in quantum computing. You know why? Because if you have a, if, I won't talk about it. If you have a system where you have a qubit, okay, qubit is like you play with the spin of the electron. Let's say, for example, you have a spin up electron, you have a spin down electron. Now, how do you change the spin of the electrons? You change it by giving a microwave signal at certain frequency. This frequency depends upon what is the tuning frequency of the spin, something called as Larmor frequency, Larmor precision, Rabi frequencies. They are the quantum mechanical concepts. Let's not go into that. That frequency exactly matches with those particular frequencies, spin tuning frequencies. And you can basically flip the spins. You can make it up spin, you can make it down spin. Once you play with the spins, you can have this qubit control. And here you have a microwave thing. And how do you generate the microwave and how do you control the microwave? There is the microwave device. And what are those microwave devices? They again go into this particular section. What microwave systems you use, whether you use a gallium nitride, aluminum gallium nitride, GaN, AlGaN, HBTs, all of those devices are going to be used in it. And why the cryogenic application? Because cryogenic means very extremely low temperatures. Because these quantum applications are right now, they are controlled at very low temperatures. You might have seen those large uh, something called as dilution refrigerators. They bring the there are disks present in that, and the final temperature of the disk is in approximately millikelvin range. So that's why you want your device to work in that millikelvin range without any degrading of the performance. So cryogenic microwave electronics is currently a very hot topic of research. People are, I mean, they are just fighting to work on this particular topic because it's having direct impact on the quantum applications. And And also these applications of people are almost entirely currently working also people are all the time working on these applications because they want to work on higher and higher frequencies, let's say beyond 100 gigahertz frequency or beyond 200 gigahertz frequency. That is essential for these defense and commercial applications. There is also one more aspect in terms of using different substrates, studying those substrates. What is the effect of using silicon carbide substrate on the thermal conductivity? Thermal conductivity is how well the heat can be dissipated in these devices. Just like if you have, let's say this is LGAN, this is GAN, this is silicon carbide. If you use silicon nitride instead, what is the effect? Okay, it can give you different effects in terms of thermal conductivities. If the if the silicon carbide is having better thermal conductivity, it can take away the heat more efficiently. Okay, that will be good for your device. You want the heat to be dissipated as fast as possible. And this is one aspect of people, one aspect of studying it, of studying the substrates, studying the materials. Another aspect of studying it is studying these interfaces, because there is something called as interfacial resistance, interfacial thermal resistance, thermal resistance. It is how the heat gets transported from these interfaces, because these interfaces are just like the barriers to the transport of the heat. Because this LGAN is having thermal conductivity K1, GAN is having K2, silicon carbide is having K3, different thermal conductivity values. So accordingly, the heat flow will be different in these different layers. So how you can efficiently get the heat out from this device is a basic challenge process. That is a very open area of research, because this boils down to, it almost boils down to the how something called as phonons behave, something called as interfacial phonons behave. How the phone, because those phonons are basically transporting the heat in these devices. Okay, phonons are just like quantized lattice vibration. So how do phonons behave at the interface is the ultimate current research, hot research topic, and it always has been, because it's very difficult to understand these phonons at the interfaces. Okay, what happens to the phonons at the interfaces is very, very essential. Yeah, you have a question, ask me. Sir, I'm a fourth year student and 2 months left to finish college. I want to do a job in I will answer your question. Just give me a moment. I'll just finish it, then I'll get back to you in a moment. Okay? Just give me a moment. Very it's a very detailed question. So, so this is one aspect. Now another aspect is looking into something called as CMOS, GaN-based CMOS technology. Why is this essential? Right now, we don't have GaN-based CMOS. We have silicon CMOS. CMOS is combining the NMOS and the PMOS for your digital applications. You make your gates, logic gates, and you do all the computations in ones and zeros. Silicon rocks there. You cannot replace silicon in the CMOS technology. Not at this stage right now. But the people are trying to work on this technology. Basically, you require faster switching applications. Switching. If you want to go from 1 to 0, 0 to 1, you want it to be as faster as possible. This is 1 0 1. You want this to be as fast as possible. For as fast as possible means you want to be in high frequency regime, high frequency switching. Let's say in 5 gigahertz, 4 gigahertz. That is what your clock frequency is currently in your mobile phones, in your not in your mobile phones, in your computer chips. You might have seen the NVIDIA chip or Intel chip that basically works at 5 gigahertz clock frequency. That is basically the switching speed of those digital devices. It is difficult to achieve in GAN based right now. GAN based CMOS devices are not, uh, I should say, practical in today's world. Why? One of the important thing is because of, I should say, because you only have n based GAN. You only have n based GAN right now. Right now, at least. N based means you have a channel of electrons only. You don't have a channel of holes. It's very difficult to get in GAN. If I showed you, you remember this is LGAN, this is GAN, and this was 2D electron gas. 2D electron gas. This was 2D electrons. Electrons. So that's why this is N based. This acts like an electron channel. You want another system where you can have a 2D whole gas. Okay, you should be having something like maybe something like iska ulta, something like this, something like this. Okay, let me show it like this. This is the conduction band, this is the valence band. You should be having a region somewhere somewhat like this so that you can have holes here so that it can form 2D whole gas. Why it's essential? Because this will act like a N-type, this will act like a P-type. So now you have a CMOS, complementary metal oxide semiconductor. You can make a CMOS. CMOS is made by CMOS is made by using a P-type device connected to an N-type device, and you can have a CMOS technology. This is P-type, this is N-type. You have the holes in the channel here, you have the electrons in the channel. This can act like a logic gate. Logic gate. If this is the output, if you give in 1, you will get 0. So this acts like an AND gate. That's why you require both P and N type here. Operation is deeper than that. You might have studied in your basics. But in the gallium nitride based things, you have a difficulty in getting the 2D whole gas. You cannot get a whole channel. There are now certain techniques come up, but they are not promising. So what people are doing, they are using gallium nitride as an N-type device, but they are using diamond as a P-type device. So the diamond has an essential quality that it behaves like as it has a 2D whole gas. Let's say, for example, if this is diamond is having huge band gap of almost of the order of, I don't think it's almost like 3.5 electron volt. So if this is the surface of the surface of the diamond behaves like this. It's bended upwards, and there is a whole concentration here. It's like 2D whole gas. So now you can combine the diamond device, diamond field effect transistor, and the gallium nitride field effect transistor. You can combine them in a CMOS technology, just like this. Just like if this, let's say here, if this is made from diamond, if the substrate of this is made from gallium nitride, you can make a CMOS. That is what this device is basically showing. This is the device. You see, this is diamond. This is this is gallium nitride. Gallium nitride. So this is GaN based device, which acts like an N type. This is P type. So you have a CMOS. Okay, this is actually from our group, from our device group, which is Applied Quantum Mechanics lab group. So they made this device last year, and this is basically CMOS technology. Now you can see how the output voltage is varying, but the frequency is still low. It's like 5 kilohertz, 10 kilohertz, 50 kilohertz, 100 kilohertz, but it's a good beginning. So you see the switching is happening at 100 kilohertz frequency, and these are the characteristics of those devices. So this is a CMOS made up of GaN and diamond. So these are trending research topics right now. And now, what are the other? This was all in electrical domain. Whatever I talked about till now. Now there is another domain which is something called as optical domain. Optical domain is a huge opportunity for people in research. It is much greater than electrical domain because in optical domain you have the ability to study the quantum mechanical processes. You have the ability to make like optical devices, just like optical waveguides, just like optical waveguides. You have the ability to make the lasers. You have the ability to make LEDs. You have the ability to make displays. You have the ability to study the quantum processes. You have the ability to model those processes. You have the ability to study phononics, high frequency phonons. I'm talking about gigahertz phonons or terahertz phonons. So you have the immense opportunity in the optical domain. So this is a very, and only few people in India at least are working on this optical domain because it requires a very sophisticated lab as well as sophisticated optical characterization techniques. It requires something called as femtosecond lasers. It requires very ultra fast lasers. It requires ultra cooled systems. It requires cryogenic systems in order to do the experiments. And then for the modeling, it requires very the high power computing or the high processing computing systems, because those in order to model the quantum processes, that is very I should say computationally heavy processes. Now, what I am talking about in optical domain, this is actually my area. I'm not showing it completely because this work is not published yet. So I'm just giving you a flavor of it. If you have a system just like this, if you have a device which is having aluminum gallium nitride, aluminum nitride, this is GaN, this is C-GaN, which is C-doped GaN, then this is silicon carbide. You can basically use something called as pump probe technique. In the pump probe technique, what you do is that you shine one light, not here. You shine this light first. This is called as pump, and the pump is like it's like a laser with a pulse width of almost 50 femtoseconds. So you see how small we're talking about, 50 femtoseconds. Okay, it's like it's you cannot imagine how small this time is. So the pulse width of this is 50 femtoseconds. You shine it on the system, Algan GaN there, and you excite the electrons in it. And with the electrons, all of the processes happen. Whenever the electron gets excited, it goes higher if the energy is greater than the band gap energy. If this is Eg, if this is E is greater than Eg, I mean H nu is greater than Eg, the incoming light. So this portion is the kinetic energy of the electrons. So now once the electrons want to come back to the bottom of the conduction band, they want to come back here. So all of those processes that happen here is called as intra-band processes. You can study them and you can see what is happening to the electrons. So there is scattering happening. So there are phonons getting released. There are optical phonons. There are acoustic phonons. Okay. There are other processes as well. You can also compute something called as deformation potential I talked about. You can compute something called as piezoelectric potential. A whole lot of opportunities open up. This is just like I'm giving you a layman overview. And now what you can do is that you can make a device that can basically control, where you can control these processes and at a femtosecond scale. Well, once you excite this with a pump, then you bring another laser, which is something called as probe, that probes this dynamics of the electrons inside the system. Okay, it is just like you have a box, you are exciting it with one laser, which is pump, and you are creating non-equilibrium population of electrons. Then you are bringing in another system, another laser, which is probe, and then probe basically gets transmitted. Then there is a detector, there is polarizer, there are all sorts of things. Then you have the signal processing systems. Then this probe basically, it basically studies the dynamics of the system. Okay, this is the open, this is always open research problem, because people have just started to understand what happens in these devices. So now with the help of it, you can study 2D electron gas, you can study energy levels, you can study phonons, you can study electrons, you can study quantum processes, you can study all of those things using this process. Okay, just like this one example. This is something called as coherent phonon. This is what actually I work on. So coherent phonon is like a phonon, but it is having a certain phase relationship. You see that these oscillations, this is real experimental data from gallium nitride, and this is from gallium nitride and aluminum gallium nitride. You see, these are the actual phonons you are seeing. These are quantum mechanical oscillations of the atoms taking place because of the irradiation of the pump, irradiation of some light, some femtosecond light. And these happen to be at a frequency of 40 gigahertz. And you can see clearly that there is a variation. So when I say coherent, coherent means that there is certain phase relationship between these points. These points. Okay. So coherent means if you have waves like this, these are coherent. There is certain phase relationship. That is the essence of coherent form. And where we are going to use it, that is a separate thing that I'm not going to completely reveal, because it's an open research problem here, and people are currently still working on it, and they have been working on it from a couple of years now. And if similarly, if you have just like if you have layers of different materials, just like you have GAN, you have LGAN, similarly you have GAN, and you have repeating it, you can basically create those phonons or certain oscillations in this pattern using the same technique. These are real phonon or quantum mechanical oscillations. Now, this is one aspect. Now, what you do is that you want to study these using the simulations or the theoretical models. For that, you have to go on to something called as quantum mechanical simulations or quantum models. You have to solve the Schrodinger equation. I'm talking about time-dependent Schrodinger equation. That basically looks something like this: IH dou psi by dou t equals to some h times, let's say, some v. This is basically something called as Heisenberg equation or whatever you call it. You have to study about the evolution of time-dependent Schrodinger equation, and you have to consider the Hamiltonian by considering the electron-electron Hamiltonian, electron-phonon interaction, electron-laser interaction. You have to consider the phonon-phonon interaction in the Hamiltonian, and all of those things have to be considered in the quantum simulation. And this is quite computationally heavy. That's why people don't usually do it, because it requires a lot of, first of all, funding to get the servers, to get the machines, and then to start simulating these processes. It takes almost 36, 48 hours or 3 to 4 days to simulate a single process quantum mechanically, because these are included in something called as many body processes. Many body process Many body process means that you don't have only one electron, you have many electrons, right? You are not talking about single electron in a system, you are talking about billions and billions of electrons. So that's why you have to solve something called as many body equations using something called as time dependent density functional theories, Hartree-Fock models. I can talk about it for almost maybe decades, but time, because of the limitation of the time, that is the essence of what that's the flavor I wanted to give you. What are the open research problems in these particular domains? So that is it from my side, and I hope you enjoyed this particular session. And I'd like to acknowledge, particularly thank the PMRF team who have been very supportive, the NPTEL team, particularly Professor Digbijoy, who gave me basically this opportunity and who selected me to be a TA for this particular course, and it's a huge thanks to him. So that's it. We are done for this particular course. I hope you enjoyed the course. You enjoyed the entire sessions, and that's it from my side. Now I'm going to take your query. Okay, what is it? I'm a fourth year student and 2 months left to finish the college. I want to do a job in electronics, but when our college did not come to electronics company, I was saying that if you give me some suggestions that if I do masters in something, I can get a job in good company. Actually, I do not understand what to do. VLSI, embedded RF communication. Okay, that's a great question. So I'll end this session and then I'll answer your question. I mean, I'll stop the recording, then I'll answer your question. Thank you for your uh, patiently listening to this session. Thank you.